the volume up because someone shows up there. Oops. It's okay. Everything looks all right. That's good. So yeah, the quiz, I guess the quiz was okay. Like everyone, like the two grad things got 100, the undergrads got an 80, but the undergrads didn't really do the derivation. One of them was okay. This one, the undergrads got wrong, but I mean, the Dubai, it should just be -2 and a Grenier, like a knee and power 2. And the data is like pretty strongly like -5/3 and then 1. So there's no 2 in it. So in the function, they have a background, which took care of the 1. And then they have that weird low Q power law thing that kind of must have taken care of the rest of it because their fit looks perfect. So it's not really possible. So those two terms are needed. If they just used the middle term and like narrowed down the fit range, they would have seen that it didn't work. So that's kind of how it goes. Let's see. So there's that stuff. So I wanted to talk about this. Well, let's see. First, yeah, there's another thing that's kind of interesting, I guess. I've been looking at asphaltenes, which is kind of a macromolecule. Let's see, how do I get that? That's going to be this guy. To what? That's homework. This thing. So, see, I'm not sure I have a picture of asphaltenes on here. It's basically a aromatic. It's like a poly aromatic hydrocarbon. This picture here. There's a bunch of papers about it. Anyway, it's a thing. I'm just mentioning it because I used that Weinstein-Zernicke equation. It's like you have so you have these are aromatic. So just keep going. That's 5, 7, I guess. That can be different things. Or you can have more rings. You can have like a ring with a sulfur in it. Maybe you can have a ring with like a nitrogen. Maybe we have rings with oxygen. Maybe we'll have like 5 to 7 carbon tails kind of hanging off. And some of those can have the hydroxyl on it. When you have crude oil, so like the Bracken shale oil in Canada is like something like 80% this. Okay, what this does, you get what you call pi-pi bonds, so or pi-pi stacking. So the aromatic rings will stack on top of each other. I guess each one is like a little coil, so they end up making kind of a field that they associate with each other and makes pi-pi stacking. So they attract each other anyway. Or you could look at it like a Van der Waals bond, like say the electrons are all over here at one point. So they have an instantaneous charge, and then that will induce a charge in the other one and pull it together. And because half the time it would be repelling, but repelling makes a distance go further. The other half it's attracting. But when you go further, it's like 1/r² dependence. So the repulsive one is less than the attractive one, so you end up with a net attraction, even though they should be equal. But because it's weighted by 1/r², then repulsion moves it apart. You end up with attraction. That's that could also be something to do with this pi-pi. Anyway, so they form these kind of clusters, something. And then somehow those things, so this is like 10 angstrom. These things are like 15 angstrom. And then those clusters form kind of networks, little networks. And then somehow there's a long road, and you get to a millimeter, and they form like a network at millimeters. You can get like SEM of. So they form like gunk. In other words, it looks like this ugly pile of black goo. That's what that Bracken shale is basically, because it's 80% this stuff. So anyway, people are interested, I guess, in that. It looks like a few people. So mostly like how do you get rid of the gunk? Because if you pump crude oil, right, this gunk forms at different pressures and temperatures. Like, all right, so off Brazil, they're drilling under 1 mile of ocean or 2 miles of ocean. Then they go get to the seabed floor and they drill 5 miles underground under the seabed floor. Total is 7 miles. So the pressures and temperature is significantly different down there than it is when they pump it up into the South Atlantic, in kind of the cold part of the South Atlantic. So that the anyway, these things are the chief culprit. Like they'll just form this gunk, this ugly black goo. If you try to pump that, it doesn't pump. You know? So it's like people have tried to figure out how to break that up so you get oil. In Canada, it's like it's absolutely disgusting, right? It's mixed in with sand. So you have like, right. So also this stuff tends to form gunk when it's in narrow pores. They have like 0.5 micron pores that just fill up with this gunk. And then it's soaked in kind of like we'd say like kerosene or something with the gunk. Yeah. So that's what the sand is, right? So they call it, so it's like a sand oil gunk mixture where they have to somehow break apart. So they have these huge steam plants in the middle of the tundra or whatever up there, I guess. So first they strip mine this stuff, which is already like kind of an insult. Then they take the strip mine tailings and they put them into these gigantic steam plants that run on coal to like heat it up to break basically. So this becomes like a huge investment problem and other problems. And also like when you pump it, so this stuff can precipitate out in odd circumstances like pressure, temperature, shear flow, like anything can make it come out, and then it's just unstable. So it just forms that stuff and clogs everything up. Right? So you
You
get
accidentally combine it with crude that's too saturate rich or too aromatic, it'll crash out and wreck the desalters at the front of the refinery.
yeah. So there's a lot to it.
That's one of the big
this stuff.
problems.
Yeah. So there, and they take like one crude and mix it with another crude or something to try to make a better crude.
Always.
So anyway, so anyway, there's a lot to it, this asphaltene thing. I only know a little bit, but basically, all right, so some French guys, so that's
Sounds like a lot of people doing, but we got this junk we don't want, we want to get rid of it.
right, but it's
Find a
essentially,
use for it.
it's a
So-
macromolecule, and if you put this into a rheometer, it shear thins. So it's like a shear thinning fluid, just like a polymer. So it's actually pretty close to polymers. Let's see, so anyway, these French guys did neutron scattering on it. So this is the kind of the reason I'm bringing this up. So they do what they call a Guinier analysis. And they do a Zim analysis.
Are you showing something right now?
Yeah, I am. To me, it's great. It's so good.
It's a great blue screen.
Yeah, this guy has a slow response time to like when you say like display it and like. Anyway, it's all right because there's like things flashing up here. It will display. I kind of have some faith that it will. It's too bad that it doesn't do it on its own though. Maybe I need to just unplug it. Settle down. This might be some kind of problem with this whole system. It's supposed to be like a supercomputer. It's like an M1 whatever. And it's got all kinds of like video, whatever.
I think you can like drag it over because
Oh,
it's like an
oh, good
extension
point.
of your
Yeah,
desktop.
thanks. Yeah,
Yeah.
thanks. That's exactly it.
Oh, slow your mouse cursor.
Yeah.
All right. No, I can't see it. I can see it here.
I know on Windows, there's a button to switch from like mirroring to.
Yeah, I can do it here.
duplicating.
Yeah, no, it's not hard to do here, but I'm not gonna do it. Anyway, this is Guinier's law, the knee thing, right?
Mhm.
And this is the data they got from it, okay, from that stuff. So you take the crude oil, you put it into, you precipitate it out with alkanes, and they dissolve this stuff into deuterated toluene. It goes into aromatics, so it's got the aromatic rings, but it won't go into the alkanes, like heptane, octane. So they got the stuff that fell out of octane, heptane, pentane. They have like 3 different curves, and then this doesn't really have to do with polymers, but it's got to do with the scattering. So it's the scattering is log log plot, IQ, Guinier's law is a knee. So they say they do a Guinier fit. Then they do the Ornstein-Zernicke fit, okay, which is this black line. It looks okay. Okay, this stuff's 2-dimensional, like it's sheets. Okay, so it kind of makes sense that it would be have a slope of 2, which that Ornstein-Zernicke has. And then, but these aren't. This isn't like whatever Ornstein-Zernicke is for, which is some unknown thing. I mean, the Ornstein-Zernicke has got to do with like correlations between odd things, like this whole Ornstein-Zernicke equation, the C of R plus integral C of R times H of R dr. That's talking about correlations of things and how they form kind of a network of stuff in space. So it's nondescript. It's some nondescript network of stuff in space. So it could describe anything, including this kind of asphaltene thing, because it's a nondescript network of stuff in space, right? So there you go. So it's kind of like the universal garbage machine. So anyway, so yeah, it's kind of 2-ish here. But then like they ignore this part, which turns out to be like -4. So that's like the surface. And then that's the thickness. And this is like a disk, you know, these are like discoidal nanoparticles. But the problem is that thing's like 15 angstrom, which would be like over here. So that's the size of your asphaltene molecule. This thing's an order of magnitude bigger, like 150 angstrom, or 15 or 20 nanometer. So it's like, and roughly you'd get like maybe 10 or 50 of those little platelets stacking up somehow into a giant discoid thing that's floating around. So this thing's super hierarchical. You start with these platelet molecules, then they're going to pi stack, and then they're going to form some kind of a disk. Then those disks are going to do something. And then 4 is magnitude larger, you have your gunk. So probably there's 3 other levels of things going on, right? Than just the. Anyway, so they're using that, and here they call it a Zim function. So they call it Zim. So we have like Ornstein-Zernicke, and then we have like the Lorentz function from the micelle people. It's the same function, and then here it's called. They just randomly call it the Zim function, which is, I mean, in the origin of that is like the Zim equation, like 1 over minus exponential times plus exponential is 1 plus q squared is 1 over I. So that ends up being the same thing as Ornstein-Zernicke and as a Lorentz. Lorentz comes from that. That's the mathematician who used that function in the 1800s or something. And then the Zim thing is from the 1950s in Brooklyn, New York, right, with the Zim equation for light scattering. Anyway, so I thought that was kind of interesting to look at that. But you can clearly see like the power law signature that they clearly ignore is this is -4. You put a line there. I think I have it, but I'm not going to show it to you because I got something else. So I got this. I think I put lines on it. It's nice to digitize these things because you can.
That's pretty clear that that's a different slope.
Yeah, I can draw the line on it. I'm going to do that display thing. Just mirror display. It'll take a second. Someplace here are displays. There's a box called mirror displays. Oh, maybe I just drag them on top of each other. Display settings. Oh, I don't know. Right now. so this isn't it. This is something else that I'm going to show. So let's see. It's going to be under recent experiments somewhere here. Oh, I got the same thing here. Sorry. French scattering. So that's so you can digitize that using that Igor data thief, whatever it is. This Igor thief thing. And you just copy the picture and just it's pretty quick. This took 10 minutes to do. You can see this is power 4, it's like straight 4. For the C8 and C7. And then C5 has a different structure. C5 has something else going on, right? So this is power 2, so C8 is like discs, it's a discoidal, so the stacking then is going to make a disc, and then the C7 isn't, it's something else. They all have about the same size of the blob. Actually, they're different. The red one is different from the green by a factor of about 3. I mean, yeah, like maybe 3 times different on the.
And this is how many aromatic rings they have in them? Or
No, there's no, all right, so the thickness, 2.5 angstrom is a carbon, right? So or 1.5, I guess, the carbon, 1.54, the same as the wind or wavelength for copper alpha. And then this is going to be about 10, that's like 15 angstrom. So this is about 10 of those rings thick. The knee here is for the thickness of some kind of plate-like thing. And it's 15 of those discoids thick if they're pi stacked, like just the shortest distance. And then the disc, and then this thing's like 150 or something. It's 15 nanometers.
no, I mean like what 5, 7, 8.
Oh, that's C8. That's octane, heptane, pentane. That's the French name of it. The way they named it in that paper. Like, so they just take crude oil. They get so it's Total, right? And so they get their own crude oil. They get it from like 3. I don't know. It's kind of interesting what they do. You wouldn't think you could do neutron scattering on crude oil, but they're doing it. So anyway, so yeah, these are the fractions that come out. So they put it into octane. Then the stuff precipitate out, and they take what precipitated out, they filter it, and they put that into deuterated toluene. So it's kind of messy, but actually the curves are really clean, considering that that's just pumped out of the ground. Like it's basically dirt, right? And all you did was, so it's kind of interesting. Anyway, so that's it for that. I guess you can see the digitize. It's not just, I mean, I do scattering, but basically digitizing anything, right? You can take and just plot it in a different way, and you can see where people are lying to you. Right? So I encourage you to figure out, you can use other programs to digitize. This one's I like because I use it for other stuff, but I encourage you to take people's, when you see something, even a report, just lift their stuff, just get the points and then plot it in different ways and see if it makes sense in some other way that they didn't even bother to really think about. Like, why didn't they think to look for Pro's law here? That's the first thing you should do with any scattering curves, look to see the surface. Like, what's the smallest thing? Like,
It's not like it wasn't there.
I mean, it's
pretty
so
obviously-
clear. It's sitting there so clearly. Yeah. So, and you expect it here, and it's clearly there. So, yeah, you're right. I mean, it's kind of strange that they didn't do that. They were at ILL, which is the best, historically the best neutron scattering place in the world. It's in Grenoble, France. So there's no reason why they wouldn't see that. I mean, it's pretty strange. I guess they were really interested in this raised gyration over
Yeah,
here.
I guess they see it, but they don't really care about it.
Yeah, well, I mean, to me, that's like so important, like how many of these stack, that's telling you directly, because that's the surface to volume for this thing. So, and then the Grenier part of that gives you like how many are in a stack. That's like one of the main points of the. Anyway, so there's that business. Oh, I hate that. This mouse is like too something.
Too sensitive.
Maybe, I don't know what it is, but it had a bunch of things set up like double click and all kinds of weird 3-4 finger or whatever, So I shut that all off and it was much better. Anyway, so I go back on this thing. We won't have that lag time. So anyway, the point today is to start going through this hydrodynamic radius, which is the other, it's the other number, So you can get the size, you can get the radius gyration, you get the hydrodynamic radius. So Kirkwood's a guy from Yale, right? And he didn't win the Nobel Prize because he's buried. You can wiki him or something. Get Kirkwood's grave or something. Then there's a guy from Yale that did win the Nobel Prize, and their graves are like right next to each other. And Kirkwood's grave is like this long list of all the awards that he won over his whole life, And the guy next to him just says Nobel laureate. That's it. So and they were like in the same department. I think it was like chemical engineering or something at Yale. Anyway, so a long time ago, right? 53 is this thing. So anyway, he figured out how to all this hydrodynamics of like this hydrodynamic radius. So the point of it is like is this: you have, so you can calculate. So you have Polymer chain or whatever it is. Then you can kind of calculate what this hydrodynamic radius would be. But so see for that object, like say you pull it, there's going to be like the velocity. There's a force that you pull it with. There's a friction factor. The friction factor is going to be related to the temperature. Stokes law times this hydrodynamic radius. So if you can get like the velocity of an object moving, right, or if you can get the flow of it, then you can get this hydrodynamic radius for the thing. So there's kind of two ways to get it. Like how fast does it move? This velocity, which is related to the diffusion coefficient, right? So like the flux is going to be like the diffusion coefficient, and then the square root of time, the square root of both of those things. So anyway, so if you get the diffusion coefficient from the velocity, then this is the that's not the friction factor, that's the diffusion coefficient is there. And this thing is it's KT over this friction factor, that thing. So anyway, you want to, this is the size that you can measure, right? Or you can calculate it for this object. So if the object is like that, it's going to have this number 1 over Ri minus Rj, and the average of that summed over all the units of the thing. It's like a double sum, 1 over 2n squared. H. And then if like R doesn't equal R, because if Ri equals Rj, then you have a problem with division affinity. Right? So you have to kind of exclude cases where Ri equals Rj, then you can calculate this Rh for that object, or for any object, for a disk, for a sphere, anything will work that way. And Kirkwood's the guy that kind of figured that out for this. Kirkwood-Weisman. And then later on, they figured out like that number was wrong, right? So they thought, well, like there's going to be some solvent around this thing, right? When you pull this thing, some of the solvent goes with it, right? Or like Zim. So Zim's assumption is the opposite of Kirkwood-Weisman, is that the whole thing is just a sphere, right? So that this RH is the R for the sphere. That's all the solvent is trapped. So it's called non-draining for Zim. And this is called draining. And usually that's called Rouse. Or you could call it this Kirkwood-Weisman. But Kirkwood can account for this, what's called the hydrodynamic effect. So the hydrodynamic effect is how much solvent goes with the thing. How much does it drain? And that can involve a lot of math, a ton of math. Like use functions to describe that whole thing. It's really complicated. Right, so we have no hope of really fully understanding that. We can understand the Zen. We can understand a little bit, understand this thing. Anyway, so it's like the Kirkwood thing is this equation, right? It looks a lot like the radius gyration equation. We had Ri minus Rj squared. We're going to get the squared radius gyration. You overcount because it's a matrix, so the top and bottom are the same. So there's a 2 here. And then it's n squared because you have to divide by n for each of the sums. So the 2 numbers you have in there. And so you have the same 1 over 2n squared here. And then this is this inverse sum of these. So this kind of inverse sum, the smaller numbers are weighted more than the larger numbers. Right? If you have 0.1, it becomes 10, and 10 becomes 0.1. So the smaller ones are weighted larger. So you expect this to be a smaller number than that. If the world's fair, I guess. So that means Rg over Rh should be a number larger than 1. I mean, just kind of obviously, because it's an inverse sum, and that's a sum of squares. In fact, the second moment should be higher than the first moment, so that should be a bigger number. Right, so it ends up being 1.5 for a Gaussian chain. This Rg over Rh ends up being 1.5. But if this is a sphere, then Rh is the radius, because this is a radius of an equivalent sphere. So it's like, in other words, this is defined from that drag coefficient, and then it's the drag coefficient comes from a sphere function. There. You have the friction factor equals 6 pi times the viscosity times this hydrodynamic radius. This is for a sphere. Right? The velocity is the force that you put on times the friction factor. So if you pull it harder, it moves faster, and this thing is then drag. Okay, that it's not proportional to R squared, it's proportional to RH. Partly you can say just if you figure out the units of viscosity, it has to be power 1 here. But in reality, it's really complicated why it's power 1. Like it was derived by Stokes. It's something like 1890 or something. So anyway, so this is for a sphere, right? So that's kind of the point. That thing is a sphere radius. So for a sphere, that thing's going to be the sphere size, and then Rg is square root of 3/5 of the sphere size. So the ratio of those two is square root of 3/5 for a sphere, which ends up being 0.77, like square root of 3/5 for a sphere. This is from 1980. Stockmeyer won the Nobel Prize. I think Stockmeyer is at Dartmouth, which is a weird little place. And then Schmidt, I'm not sure which Schmidt that is. Burchard's a French guy. So anyway, so 0.77 for a sphere. And then for Polymer, they figured out that it was this 8/3. 8 by 3 pi square root of pi is about 1.5. And then if you have like a randomly branched structure, 1.73. So it gets, if you have these open fractal structures, you get numbers bigger than 1, and solid things are numbers smaller than 1. For so you can. Anyway, so I needed to do this for something else. So I programmed those equations, to see how they worked out. Oh, this guy's asleep. All right, then maybe it's already open. This is already open. So that's the equations. But this can't be the right thing. Let's see. This is the right thing. I guess it's in the same thing. Oh, this is the program here, right? So calculate RH is just like do this inverse sum, whatever it is. So it's, well, this is get RG, so it's like the squares, the sum of the differences squared gives the RG kind of eventually when you divide by 2 over n. And then for this thing, you have to say not when the two are equal, because otherwise you get infinity, which I found out by doing it. It kept coming out infinity or 0, or 1 over that would be 0. So if you say they aren't equal, they just have the difference. You sum up the differences. So you have to calculate the two vectors and square them and take the square root to get the difference in the vectors. So anyway, so you can just, it's pretty easy to write a thing to do that. This makes a block full of points. I have these 3 things in here. Oops, that's what I mean about the mouse. Why did it do that? This makes it like a micro. Let's see, this is this mouse. All right. New 3D. Ask me. Oh, I know. It's not there. Wow. This is what I want. A cube. Doesn't let me make a plot here. Oh, I figured out how to do this the other day. This isn't it. Display. Oh, here, there it is. All right, so that's a cube, right? I wrote a program to make a cube because I wanted a sphere, but it's easier. That's a cube. Let's see. Then this is. That's a rod. Right, and then this is a random walk where it worked out to be. It's a random walk where it worked out to be that the end-to-end distance was NL squared. You know, so it was a random, because if you do a random walk, it doesn't always come out to be that. So that's one that's right size, and then so there's a cube, that a rod, and a chain. And there's also a odd thing is the thing that I wanted. This is just an aggregate. It's like a piece of dust particle. It's actually silica. It's like a silica thing. So there's those 3 things. I mean, you could run that program to do those. There. So that program's like here. So it doesn't come out exactly right. So anyway, it comes out like there's a factor between the numbers, that between the RG equation and the actually you can see it so much better here. Like if you do the cube, this comes out to 0.29 and it's supposed to be 0.77. So there's a factor of 0.38. And if you multiply that by the number, like for, if you multiply that 1 over 0.38 is 2.6. So if you if you take the numbers that you get for R by H, RG by RH, for the others, they come out to be the right number. Like this should be 1.5 for the Gaussian coil for the 1.46. It's not a perfect Gaussian coil, and for the rod you get 3.73. So anyway, so that it kind of works, but there's a. Yeah, I wondered if that actually works. So that's the point of that. So you can do it. So this kind of works. So you can predict these things. And they match up roughly with these numbers, but there seems to be a prefactor missing, like the RG and RH, they need kind of a prefactor. Probably the RH needs a prefactor to get it to be the right number, for this equation. But the trend is right. In other words, if I have 3 of them, I know what the answer should be, and I get 1 to match, the other 2 match. So it's just a prefactor number. So anyway, you can do that. So this is how, so you can calculate this hydrodynamic radius, right? That's kind of useful. Then you can get that ratio and you can measure both, right? So the question is like, how do you measure those things? So there's 2 ways, it's kind of like 2 ways to measure this, right? So there's 2 main ways to measure the hydrodynamic radius. So one is using that Stokes-Einstein. So you take your solution. Again, you can do this in a column. So if you have a GPC column, so called high pressure liquid chromatography or gel permeation chromatography or size exclusion chromatography, they're all the same thing, kind of. Although they'll have different meetings, like each one will have their own meeting. But basically, SEC is kind of a chemist thing for like asphaltene, HPLC, GPC is polymers, this is chemist, and HPLC, I think is both or something. So it's kind of the same machine. It just depends what column you stick in it, more or less. There really are 3 different names and the 3 different groups that really do this stuff. Anyway, so you separate that out, and then it comes over here, and you can run it through. I forget the name of it, but it's an equivalent of a Wheatstone bridge. So you run your sample. And you have a solvent pool here, so you compare the time that it takes to go through the 2 things. Right from that, so if you have the flow rate coming out of this thing is going to be proportional to viscosity times the time. Then if you measure the time, you can get the viscosity from it. This is kind of Stokes' law. Right, so if you have the viscosity is the solvent viscosity times this improvement factor because of your stuff. Right? So this thing has to do with how your concentration. So it's going to be like 1 over concentration, and then how that enhances the viscosity. And so this thing is going to have units of inverse concentration. And it's called intrinsic viscosity. So anyway, so anyway, you can swap out. So if you have the time for these things, so you have this upside down. The flow rate, the longer the time, the higher the viscosity. So it should be, it's like inverse to this. This should be inverse. Anyway, so viscosity proportional to time, put it that way, how that works. So anyway, so you have time and time, so you can take the ratio of the times, T over T0 minus 1. And then if you divide that by the concentration, you get this intrinsic viscosity, as long as your concentration goes to 0, because you don't have effects of binary things like these other terms. So that's the idea of this thing. You can get this intrinsic viscosity. So what is it? Well, so this thing's like concentration is mass per volume. Right? That's what the concentration is. So you're going to have the mass. If you have a polymer coil, you have NL squared is R squared. So you're substituting in this R. Yeah, and then you just have like RH here. So you have the volume of the thing, right? So basically this thing's going to be like, could be done in the molecular weight So R goes with the molecular weight to the 1 by dF. So you could say that this thing, it's gonna be volume for mass, right? So if the volume is R cubed, then it's gonna be mass to the 3 by dF minus 1. Or you could do it in terms of the R. So it would be R to the 3 minus 1 by dF. So this number, this intrinsic viscosity is going to be proportional to molecular weight. Yes, since you're trying to get molecular weight usually. And if dF is 2, it's 3/2 minus 1 is 0.5. So and if dF is 5/3, and you have 9/5. 9/5 minus 5/5 is 4/5 of 0.8. Like 4/5 is 8/10, 0.8. And if dF is 1 for a rod, it's 2. You get quite a wide range, like a rod to a Gaussian coil is from 2 to 0.5 for this thing. So you definitely tell a rod. Telling these two is a little bit more tenuous. And so anyway, that's kind of the rules for this intrinsic. That's called the Mark-Planck equation. This kind of viscosity goes from to some power, and the powers can have to do with this kind of structure of the thing. It has something to do with what the structure is. So how does that relate back to the hydrodynamic radius? That's a good question. So that's that business. There's Pucell's law done properly, except it doesn't have time in it. Let's see. I mean, the radius of that is the hydrodynamic radius. It doesn't actually have that written out here. You know, the section's about hydrodynamic radius, but never actually wrote that. So if you calculated R from that thing, it would be nice if I had done that, but I didn't apparently. So basically, this H is a hydrodynamic radius that we use on there. It's end-end distance. It's a drag. It's like assuming like a Zinn assumption. But this R, whatever it is. So if I write the intrinsic in terms of R, it's going to be a hydrodynamic radius. So I could say that the intrinsic viscosity to 1/3 minus 1/dF, and often 1/dF is called nu. So it would be like intrinsic to the 1/3 minus nu. This nu came about before they knew about dimensions. Like it was just a number, a scaling number. Actually, it's Florey invented nu. And then in like 1960, and Mandelbrot invented this idea of DH like 1970 or something, the end of the 1970s. So there was a gap between like talking about things in terms of dimension, just saying it's a scaling number. So you'll see like in Florey's book, he'll talk about nu. It's 1/dF. It's always the same thing. So anyway, this intrinsic 1 over that is going to give you this hydrodynamic radius. If you measure that intrinsic viscosity, which is simple to do, so you can do it for each fraction of your coming out of your column, and you can get the hydrodynamic radius from that. Or you could get the molecular weight from that too, if you knew what this Mark-Planck coefficient was. Right, so this is kind of a useful thing to do. So often you'll have, if you have a full GPC, like you bought every bell and whistle on it, then it'll have a light scattering, it'll have an index, which is like the standard thing, a light scattering, a viscosity measure. And then, that's it. Right, those three are like the things that you get on a GPC. The viscosity thing is pretty robust. The light scattering fails sometimes, and this intrinsic thing is just shooting the light through it, so it's no problem. So terms of robustness, probably the intrinsic and the viscosity are the best. The light scattering is a nice thing to get the molecular weight out of it, but basically a lot of times it isn't working. So, so that's one way. The other way to get it is to do dynamic light scattering, which is sometimes it's the same machine that you're doing light scattering with. So you have like Brookhaven Instruments makes a machine for this. So you have a laser. It's not a high power laser. It's like a helium neon laser, and there's a big bath of toluene. And then you have in the middle a cylindrical sample area. So the beam comes in. The idea is put the sample in the middle and it's going straight through 90 degrees to the wall. So there's no reflection. That's why everything is like cylindrical. So you come in with a beam, hit something here, then everything that comes out goes directly through. So there's no reflection off it, as long as you're exactly at the center. Then in the middle, you stick like a tube with your stuff in it. Usually it's like a liquid. And then you can pick up at the angles, you can pick up the intensities, and get the intensity as a function of Q. Right, so you can get like Guinea's law, you can get this plot from that one. That's the static light scattering. And then also there's this feed out from this photomultiplier tube. So photomultiplier tube is it's got a phosphor in the front, light comes in, phosphor gives off electrons, and it's got this cascade of the electron plows through and makes more and more electrons. So for each one electron that comes off the phosphor, it amplifies it. So a multiplier tube. So it's in a vacuum tube. You can get like 100,000 amplification of the one electron from that thing. And it's proportional. It's a proportional instrument. So that's good. The other option is a photodiode. Usually this thing's more sensitive. So anyway, you have a photomultiplier tube on the thing, and that's can read out in like milliseconds time scale. Right? So you can have the signal coming off this, and if your beam comes in, and then your stuff is kind of floating around, right? So it'll go in the beam and out of the beam. So the pattern that you get from that is like fluctuating in time. Right? You get this kind of fluctuating pattern, and so the fluctuations get bigger with KT, and they get smaller with the diffusion coefficient. Right, so it's kind of the amplitude of the fluctuations, and the time scale has to do with kind of the distance of the thing. So you can get the so basically you get these fluctuations that come out. So this thing isn't going to be a constant signal coming out. It's got these fluctuations, kind of you measure on seconds, and then you can basically convert that through Fourier transform. So say you just had one, so you just had like one oscillation in this, and that would transform to one frequency. But because it's like a noise pattern, it's going to be a decay. So Fourier transform of that is going to be this decay pattern. The decay of that thing is going to follow an exponential related to the diffusion coefficient, KT. And this, the diffusion coefficient you get from that thing is going to be Stokes' law. Given you this hydrodynamic radius, some viscosity. So this DLS machine will give you the hydrodynamic radius, and the flow thing will give you the hydrodynamic radius too. So there's two ways to get it. This one's much easier. This one is just like stick the stuff in the solvent, make sure there's no dust in it. Then push the button, you'll get this noise pattern. Then it does the Fourier transform for you, and it spits out hydrodynamic radius. So you can put anything in this. So you can put milk into it. We do the lab for milk. It's got like colloidal things flying around. You can give a size of them pretty easily. Doesn't take long. It's like absolutely the simplest thing to run. The only problem is everything has to be kind of clean because dust will like interfere with the signal from it. So it's kind of a nice, it's also like, basically ends up being a black box. You stick the thing in, you get the number out. So it's easy to mess up with a DLS too. Like you can get multiple decays, like there'll be a single decay, there can be another one here. So you can get two size scales. Say if you put in one like my cells into it, well, they have like a relaxation that way and one that way. They have two time scales. You can pick apart the structure of the shampoo if you want. But it depends on your interpretation of what this decay pattern is, you know. So, so I'll talk more about DLS. You know, 'cause it turns out that it's tied into a bunch of other techniques people use, but it's kind of the first of a series of time-dependent measurements people do to look at kind of how things relax. You can get a relaxation time. In other words, this plot of intensity or transformed intensity, which is a correlation function in space and time versus frequency, gives you a relaxation time. You know, each one of these is going to be an exponential decay. That's relaxation time. So you get a relaxation time from this machine. If you do this with different kinds of radiation, you get you get smaller time scale relaxations. So if you're looking for like a polymer, and then it's got like local relaxations on the chain, and it's got the whole thing moving around has a relaxation time, and then whatever conformational relaxations. You can pick all those out with curves like this from different machines that are basically the same idea, like see the squiggly curve, transform it, get this decay curve, and get the relaxation time out of it. So I'll go into that in more detail. Like it's worth spending some time looking at that.
But just using like, you know, different wavelengths of light or like X-rays or.
Yeah, neutrons. X-rays are problematic because the time scale and the detectors don't match up very well. So neutrons, you can play tricks with it.
Just slow them down or speed them up.
No, with the instrument. So you have like neutrons you can polarize. So they can have a polarization. So they can have a moment, a polarization moment, like magnetic moment, and then you can polarize the neutrons coming in to have a certain magnetic moment, and that has a precession, like in an NMR. Like you put a big magnetic field on a nucleus, then the nuclear moments like point in the field, okay, and then you hit it with a radio wave, and that makes it precess, so it kind of wiggles, right, with a certain frequency, and that generates the same radio frequency off it that you pick up. That's the NMR. So neutron also is a neutron. I mean, it's a neutron that's doing that. So there's a neutron, except it's just a bare neutron come out of a nuclear reactor flying down a tube, right? So it can be polarized to be pointing in a direction, and then you can, when it hits the sample, it can be depolarized by the motion of the atoms in the sample, like it's hitting the nucleus. If the nucleus is moving around, that polarization can shift, and then you can have a detector that is like almost like a Polaroid. They can tell like how much it shifted and the time that it interacted. You get the time of the relaxation from it. There's two ways. That's one way to do it. You know, it's complicated. It's not. This is pretty simple. Like you see the wiggle thing. But you can see this, the wiggle thing. The wiggle thing, yeah, so it's kind of more fun than the so there's a lot to talk about with this, but basically the speckle pattern. Here, that'll open. Might open it. Did it do it? It's going to YouTube. It'll work on my computer. Just a picture of the. Oh, now it won't do it at all. It opened this in the background, right? Very weird. It's a YouTube thing. It says browse YouTube. I mean, I can browse YouTube just for. I'm not sure this. Anyway, I can get it on my computer. What is it?
There's two URLs in there.
Oh,
It's YouTube, and then there's www.youtube.com is in there twice.
that is pretty weird.
I don't know if it's his link or
Yeah,
if it's YouTube.
I don't
that's
know
doing
either.
that.
Right.
Oh, wait a minute. I did the wrong one. I got it on mine. It's not much to look at. Slide that was way down somewhere.
That's that.
Probably all the old ones.
Why doesn't every home in the US have solar?
I don't know.
The
why.
reason is not about sunlight or weather or even politics.
So that's a laser going through a sample of like a colloid. You can see it's flickering. That's it. That wasn't really worth the time, but basically it flickers. If you detect that at one spot, that flickering
For
is
hundreds
like
of
an
years,
erosion.
analog computers were the most.
So anyway, that's that. So I'll go through that. You know, I'll have time to go through that. So some detail. Anyway, so yeah, that's it for today, I guess. Quit with me.
And what's the room number?
758.
Oh, shoot, I'm glad you asked that, because I thought it was like. It's not the one room?
No, because that was booked for a different mission.
Oh,
Like all of the